Chemistry time.
Oh, wait, did you start?
Yeah, chemistry time.
Did your whole speech about Tyler being sad?
No. Chemistry time, we're going to talk about
Please do not cut that out.
chemical equations. Chemical equations. Remember from chapter, I think 2, about physical and chemical changes. What was the difference between a physical change and a chemical change?
Chemical change was like with the equation.
Yeah,
that
we...
happened non-chemically, and like physical is like the appearance of a change in color.
Okay, yeah, so physical change is a change in appearance, whereas chemical change, we could be more specific. Chemical change involves what changing?
Composition?
Yeah, the composition. So in a chemical equation, we're going to show how the composition of one thing changes. And another word for a chemical change you probably know is a chemical reaction. Chemical reaction, which we sometimes abbreviate in this way. Capital R, capital X, capital N. So a reaction is sometimes abbreviated RXN. Reaction. Let me break them. How close can I get? Yep, RXN is the standard abbreviation for reaction. So a chemical reaction can be expressed. We did one in earth science this morning. You remember it? Tyler, do you remember it? What? The chemical reaction that we had in earth science this morning?
We did in a lab today?
No, that we did, like I wrote it on the board. It was a chemical reaction. It was...
CaCO3.
That one we could have, but we did this one. CO2 plus
H2O
yields. Do you remember?
H2CO3.
Yeah. Good. So we're just going to use this as, this is called a skeleton equation. In fact, this is both a skeleton equation and a balanced equation. But we can also write it as a word equation. So how would we, just from that vocab word, we would write carbon dioxide.
Plus water.
And we generally still just use the symbol plus water. Yields, the word is pronounced yields. What is this thing? Well, it was
Carbonated water.
carbonate, right? And it's an acid because it has that. So what kind of acid is it? 8 turns to ic, so carbonic acid. So this is the word equation. This is the skeletal equation. And then we're going to point out what the different parts are. Obviously, these two are easy. What's this one? Well, no, this is the plus sign. What's this? Yields. These two things, in this case it's 2. There can be 1 or there can be 101, but these things on this left side are called the, what is it? Reactants. Whereas everything on this side, which in this case is 1, but there can be, like I said, hundreds, products. The reactants are the things that react. The products are the things that are produced. That's as simple as that. And the products are always on the right side, and the reactants are always on the left side. So in this case, carbon dioxide plus water yields carbonic. Do you see why, I just told you yesterday, but do you see why it's still important that we know how to name and write formulas for things? Because we go back and forth between these two all the time. And if you don't know that this is carbonic acid, you're never going to get this whole thing right. Do you see what I mean? So you still have to know how to name things, like we did in the last couple chapters. And obviously part of naming things is that you have to know when to name it as an acid, like this, when to name it as a covalent compound, like this, or if it's an ionic compound, you have to name it as an ionic compound. Okay, also, we sometimes use this symbol, not quite yet usually, but if we see this symbol, it means it is in equilibrium with. And just looking at the symbol, what do you think is going on in the reaction? Yeah, it can go this way, but it can then reverse, right? The things that were products can also reverse and become reactants. That just means that both of those reactions occur at the same time, and there's an equilibrium. And then the other symbols that we quite often use, if I were to write this next to the CO2, what does that mean? This is supposed to be the letter G.
gas.
It's a gas. And this we would write an L next to because it's a liquid. And then this we write AQ, and you saw this on your last test, and AQ means aqueous. Yeah, means it's an aqueous solution, which is dissolved in water. So the little g is a gas, little L is an S, is a liquid, the little S is a solid, and then the AQ means it's an aqueous solution. Gas, liquid, solid, aqueous solution. And aqueous solution means it's been dissolved in water. I'm trying to think of another chemical reaction we could do that wouldn't be balanced, because really this stuff is all pretty simple, right? I mean, we're just naming the different parts of a chemical equation. You might have to do some work to memorize what these mean, and you still definitely, all of you have to work on naming and writing formulas for things. But in general, this is either easy stuff or it should be review, right? But now we're going to move on to, and this should be review too from physical science, but we're going to move on to balancing chemical equations. So write that as your next little subheading, balancing chemical equations. And the point of balancing chemical equations is that we have to have the same number of each element on both sides of the yield sign. Balancing chemical equations. And our goal is to get the same number of elements, we'll say of each element on each side of the yield sign. And what is what physical principle that you probably remember? Okay, well fine, run away. Okay, what is the physical principle that you probably remember that tells us this has to be balanced? Why is it not okay to have 1 aluminum on one side and 19 aluminums on the other side? Because it would violate the law of what? Yeah, say it louder. Conservation of mass. The law of conservation of mass means that there has to be not only, if we have 112 grams of reactants, how many grams of products do we have to have? 112 grams. It has to be the same. But also, if we have 60 grams of aluminum and 30 grams of oxygen on one side, we still have to have 60 grams of aluminum and 30 grams of oxygen on the other side. So it's not enough to say that the products must have the same mass as the reactants. Every single element must be the same amount on both sides of the equation, right? Because they can't change. The elements are, at least for chemical equations, they're immutable. There are nuclear equations where the elements can change, but we're not dealing with that right now. So for chemical equations, we have to have the same number of each element on each side of the yield sign. So let's do this one. Al, aluminum, like I was talking about, plus Br2 yields AlBr3, right? And
So you need one more.
well, yeah, hold up, because I'm trying. So we know, why do we have to have Br2 here? What's up with that? What do we call this kind of thing? Why is it not just Br? Yeah, there's 2 of them, but why do there have to be 2 bromines? Because it's, what is it?
It's ionic.
No, it's, remember there are 7 of them?
Oh, it's the di...
Yeah, it's diatomic. So bromine is one of the diatomic things. And then this is, what's the name of this? Aluminum bromide, but it has to be AlBr3 because each bromine is -1 and the aluminum is +3. Remember that? So that way, what I'm trying to illustrate to you here is that even if we had written out the word aluminum plus bromine yields aluminum bromide, you have to be able to write from those words, you have to change it to this, okay? So, as Natalie was getting at, we don't have the right number here at all. You cannot, write this down somewhere, I'm not going to sully my board by writing it, but you cannot change the subscripts, right? You cannot change the subscripts when you're balancing these. What can you change? Do you remember?
You can add another.
the coefficients. We can only change the coefficients, which, like you say, that adds more. So we can change the coefficients. In fact, in this case, there are no coefficients to start with, and so we can add them in. So, and the coefficient, what is the mathematical operation between a coefficient and a subscript? What do we do with those? We multiply them. So we have 3 bromines here, but only 2 on this side. So what can we multiply them by to make them the same?
3 and 2.
Yeah, we have to multiply this one. I'm going to do this in a different color. We have to multiply this one by 3 and this one by 2. And that gives us 6 bromine altogether because 3 times 2 is 6. And 6 bromine over here because 2 times 3 is also 6.
And that means you have to add 2 to...
That means we have to also multiply the aluminum. Because if there's no subscript, what is the subscript that's understood to be here? 1, right? It's not 0. And then we say that this equation is balanced. This equation is balanced. We're going to do another one of these. Ready? So this exact thing might be given to you on a test. It would be words. What should we write? What's the first step of this? Right, we have to change them first to
letters.
yeah, formulas. We call them formulas. So we'd write CO, as Jasmine says. CO. Keep going. Try one more time.
CO2.
Plus O2, because it's diatomic. Oxygen gas is diatomic. Yields CO2. Balanced? Yes or no? Try again.
No, it's
You have to
not.
put a 2 in front of the CO. But then, yeah. That's 4.
Now we've got 2 carbons, though. 4 oxygens and 2 carbons. So,
2.
where?
Over.
Here?
Right? Yeah. Right? Yes.
Well, let's count them up. 2C, 2C. Altogether, there's 2 plus 2, which is 4O. And here we've got 2 times 2, which is 4O. So yeah, that's balanced. Let's do one more practice one on the video, and then I'm going to give you guys some practice problems to do. Practice problem 4 on page 287 says, you have a question, Jazzy?
Yeah. Why is that only 2? Oh, 4. Okay, no.
Yeah, because you have to add them together. On 287 it says, in water, iron 3 chloride reacts with sodium hydroxide, producing solid iron 3 hydroxide and sodium chloride. What should I do first? So this is all what? What do we call this kind of equation given to us in 4? Word equation. Oh, word equation. Yeah, it's called a word equation because they're giving us words, right? And so we need to first write what's called a skeleton equation, which is the formulas, but it's not balanced yet. So how do we change this word equation to a skeleton equation? Tell me what to write.
And which word are you reading from?
I'm on number 4 on page 287. So once again it says, in water, iron 3 chloride reacts with sodium hydroxide, producing solid iron 3 hydroxide and sodium chloride. So I would write Fe.
3.
No.
FeCl3.
FeCl3.
Plus Na.
Isn't that like an acid? Sodium hydroxide?
It's a base. In a... You know what hydroxide is.
Oh,
Yep, OH. Yields, because it says
Yields.
produces.
producing solid iron. Fe. Isn't it OH3?
Mm-hmm. There's one more.
And sodium chloride, so NaCl.
Good. I hope you see also what happened here. We haven't gone to this yet, but we will in the next lesson. But what did these basically do? It was iron 3 chloride and sodium hydroxide, and now it's iron 3 hydroxide and sodium chloride. They basically did what? Switched. Yeah, they spun their partner around and around. This is the do-si-do. So we've now gone from the word equation that was given to a skeleton equation. What must we do now to balance it? Well, we have to balance it.
So
The neat thing about this, and let me tell you a little hint here. Do you see this as hydroxide? Hello, I'm hydroxide. Do you see him? If this hydroxide is still hydroxide on the other side, you can just treat this whole polyatomic ion like it's an element. Okay? So you don't have to count the O's and the H's separately unless it changes. And that's sometimes, with this one, it doesn't really make any difference. It wouldn't be that hard if we didn't do that. But sometime it'll come along and you'll be like, oh, this is hard. But if you just treat these polyatomic ions like this whole little chunk here is an element, it makes it a lot easier.
So you need 3 in front of your NaCl.
Okay, 3 in front of NaOH, and someone else said 3 in front of NaCl.
Right? And that's it?
And that's it. 1 iron, 3 chlorine, 3 chlorine, 3 sodium, 3, I'm going to call it hydroxide because it is, 3 hydroxide, 3 hydroxide. We could also do 3 oxygens and 3 hydrogens, 3 oxygens and 3 hydrogens. But you see what I mean by the hydroxide we can just treat as its own little lump. You have questions about how to do this? I think you remember these from physical science, right? Some of this stuff I can tell you remember, so. You have any questions then?
No.
All right, bye.